All right, today the goal is to focus on both present and future values of income streams. We're actually going to jump ahead into chapter 9 and consider discrete income streams where you have a finite number of payments and introduce an idea called a geometric series in that context. And then we'll go back to chapter 8 and we'll talk about continuous income streams where we actually have to do integrals again. But let's start with discrete payment streams. It again is all based on the compound interest formula. B equals P times 1 plus R over N to the NT power. B is your future balance. You could call it your future value. P is your principal. You could also call it a present value. N is the number of compounding periods per year, and R is called the nominal annual interest rate. T is time in years. Take N to be 1 to keep things simpler. Take N to equal 1 just keeps things simpler. We'll get B equals P times 1 plus R to the T power if N is 1. And that's equivalent to P equals B divided by 1 plus R to the T power, which you can also write as B times 1 plus R to the negative T power by definition of negative exponents. Okay. This again gives you the future value. The B represents future value at a certain interest rate R. And the P down here, if you use this equation, gives you the present value. But what again we want to do this today is use this for more than just one deposit or one amount. We want to consider income streams, many payments possibly. What's the present value of all those payments or the future value of all those payments? This is very, very useful, okay? So again, that's the context, is to consider present and future values. We will mostly consider where our interest rate is given as an effective annual interest rate. The book does give formulas for continuous interest rates, and hopefully we'll have time for that, but I didn't quite have time in the first class. Hopefully I'll have a little bit more time for that with you guys. Consider an example. Oh, pretend your grandma gives you $100 for your birthday every year. Today's your birthday and your grandma's already given you $100. Okay, ignore that $100. You're thinking about the next 3 $100 payments she's going to give you 1 year from now, 2 years from now, and 3 years from now. This is time in years. So she's going to give you $100 at time 1, $100 at time 2, and $100 at time 3. And you're wondering, maybe because you're a savvy kind of investor, maybe you've gotten into investing in crypto or something, and you're like, I want to take grandma's money and invest it. And you're like, Grandma, how about instead of giving me $100 here, here, and here, you give me just some amount right now? Because I want it now because I want to invest it now. What's the present value of all those monetary amounts is the question. How much should she give you now? Now, to keep things simple, we assume a constant interest rate because it makes things simpler. Now, of course, in reality, if you are really investing in crypto, it's like the stock market. There's not a constant interest rate. The value of your crypto goes up and down and up and down, hopefully mostly up. But it's very volatile. In the long run, you might be able to use a constant interest rate as sort of an average interest rate. But over the short run, it's not going to be accurate. Grandma says, okay, I'll give it to you, but don't invest in crypto. Invest in CDs instead. What's a CD? It's not a compact disc. Do you even use compact discs anymore? Not a DVD, not a Blu-ray, not a whatever. It's a, you want to say? Certificate of deposit, right? It's essentially a savings account with a little bit more interest. They do throw in a wrinkle that you have to keep the money there a certain amount of time without withdrawing it to give you that little bit more interest. And these days, you know, interest rates are really low, but let's pretend you got a moderately large one of, say, 2%. R is 2%, 0.02. By the way, percent, if you've never learned this, percent means per 100. Cent is like, you know, century, 100. 2% means 2 per 100. 2 divided by 100, really, which is 0.02. Another name for 0.02 is 200ths. Remember adding on the th at the end, 200ths. It's 0.02, 2%. That's why we move the decimals to the left 2 spots when we convert to a percent, from a percent to a decimal. What is the present value of these payments? You have to use this formula here for each payment individually. And they occur at 3 separate times. So when I use this formula for each of these payments, there are different T's. We say these amounts are discounted back to the present because when you use the formula with b equal to 100 in all 3 cases, the present value is less than 100, discounted. You'll hear that kind of phrase, discounted value, present value. The first payment at time 1 goes back in time by 1 year to the present. The second payment, 2 years in the future, has to come back by 2 years to get to the present. And the third payment has to go back by 3 years to get to the present. So I use this formula 3 times, but with 3 different values of t. For the first payment, I'll think of it as dividing here. Divide by 1.02 to the first power. Yes, that is the same as multiplying by 1.02 to the negative 1 power. Either way you think about it is okay, and you should feel comfortable either way. Second payment of $100 has to go back in time by 2 years. Divide by 1.02 squared. Third payment has to go back in time by 3 years. Divide by 1.02 to the third power. And since you keep dividing by bigger powers of 1.02, that means you keep dividing by bigger numbers. As you go along here, these numbers get smaller. This last one, the present value of the third payment, is going to be the smallest. The farther in the future an amount is, a given amount is, the smaller its present value is going to be, because you're dividing by a bigger power, in this case of 1.02. All right, let's go ahead and calculate these. 100 divided by 1.02 is this. And yes, if you want to confirm, that's the same as 100 times 1.02 to the negative 1 power. It is a good idea when you're doing this by hand with calculator help to keep more decimal places here. We are going to round to the nearest cent at the end, but before then we should keep more decimal places, say maybe this much just to play it safe. You can actually get away with a little bit less, but just to play it safe, let's say that much. Then we'll round to the nearest cent at the end. So that's the first term. The second one is a little smaller. And yes, that is the same as 100 times 1.02 to the negative 2 power. 96.116878. And the third one is yet a little smaller. 94.232233. Again, I'm doing it 2 ways in each case just to show you you get the same thing. Of course, when you actually do it in your homework, just do it 1 way. Add these up now. And again, I'm using more decimal places than I have to, but oh well. So the nearest cent, you get a little less than $300, $288.39. That is the present value of all those payments. But what does it mean? It does not mean this. It does not mean if you took this amount at time 0 and invested it at 2%, you get the same amount in the end. You get $300. It does not mean that. You actually get a little more. How much more? Well, let's go ahead and compute it. If I took 288.39 and multiplied by 1.02 to the third power, effectively using this formula to find the future value, I'm going to get more than the amount Grandma gave me. I'm going to get more than 300. Watch. Yeah, a little more than 300. 306.04. So what's going on here? Why do I get more than Grandma gave me? You want to say?
What you're essentially doing is you're taking instead of pulling stuff back, you're taking the one, you're taking the first year and the second year 100, and you're pushing them forwards.
That's the way to get the equivalent amount. You're right. To get the same, so this 288.39, if I invested it at 2% at time 0, would grow to 306.04 at time 3, which is not matching the $300 Grandma gave me. But as David said, if I took this $100 at time 1 and invested it for 2 years, and the $100 at time 2 and invested it for 1 year, and then took this final amount of 100, those would add to the same amount. Let's see if that happens. $100 at time 1 grows for 2 years, multiplied by 1.02 to the second power. $100 at time 2 grows for 1 year, and the $100 at time 3 doesn't have any time to grow. Does this give the same answer? The answer is yes, it does. This gives 104.04 plus, do that one in your head, 102 plus 100 does give you the same answer, 306.04. These two things match. So the point here is these amounts are equivalent as long as in both cases you're thinking about investing the money. In both cases, you are thinking about the time value of money. The $100, 300 total that Grandma gave you is just a nominal amount. It's not taking the time value of money into account. These calculations take it into account. All right, so that's what would happen over a 3-year timeline. But your grandma says, you know, I want to keep giving you $100 on your birthday for many, many years. Now, hopefully your grandma lives a really long time, maybe until you're in your 50s or something. My grandparents died when I was in my 20s and 30s, so it didn't work for me. But maybe your grandma says, okay, I'll give you $100 for 20 years instead of 3 years. And maybe even if I die, you'll still get $100 every birthday from my will, right? So if I wanted to figure out present values and future values in that context, I'd have to do something similar, except I'd have 20 terms instead of 3 terms. That would be a lot of work. I mean, I could do it, but it would take, well, about 6-7 times as long or so. So what's better is to probably use technology in a fancier way. We could use Mathematica, and we will, but I do want to teach you about spreadsheets today. Did I hear an Spreadsheets can be fun. I want to try to convince you that they're kind of fun. Some of you have not used spreadsheets. That's okay. We can learn. We will want to pay attention to things I say carefully here. We will get some practice in this chapter using spreadsheets. And it is a good thing to learn how to do. And by the way, this is my experience in ordinary business workplace, if you can use spreadsheets in even basic ways, like even to add a list of numbers, people are like, wow, you know how to use a spreadsheet. Let me give you a raise. I'm serious. They are typically pretty impressed, even if your use of it is pretty basic. So here's a spreadsheet. This is a Google Sheets spreadsheet. You know, in Microsoft Word, Excel is the spreadsheet. They work pretty much the same way, though. I will share this document with you. You see a bunch of different cells. It's kind of like Battleship. In cell A1, column A, row 1, I decided to type annual interest rate R. Let me type in the actual value of the annual interest rate in cell A2, 0.02. And it will treat it like a number that I can do arithmetic with. Let me go down to cell A4 and type time t. And then in cell A5, I'm going to type a 0. Now let's have a little fun. In cell A6, I'm going to type equals A5 plus 1. That's going to take whatever number is in A5 and add 1 to it. 1. 0 plus 1 is 1. But if it were a 10 instead of a 0, the next one would be 11. If it were 17.2345, then the next one becomes an 18.2345. Fun, fun, fun. Okay, let's go back to a 0. More fun. Click and drag this formula downward. You can copy and paste it, or just click and drag the lower right corner like this. And what happens? The formula gets updated. In cell A6, I typed what you see there, equals A5 plus 1. In cell A7, you see an equals A6 plus 1. I never typed that. It automatically converted the A5 to an A6. So now instead of 0 plus 1 equals 1, it's doing 1 plus 1 equals 2. And in A8, you see an A7 plus 1. The equal signs, by the way, need to be there to specify you're doing math. A7 plus 1, I never typed that. The spreadsheet was programmed to convert the A6 from cell A7 to an A7 in cell A8. But it does 2 plus 1 equals 3. All right, remember Grandma's doing this for 20 years now. There we go. I click and drag the entire column. I got down to 20 there. Let's type payments in this column. Although let me put a constant payment up here, just to give me the flexibility of making changes if I want. I want to put my interest rate and say my constant payment up here, just in case I want to make changes and make everything else get updated. That's the real fun of spreadsheets and the real power of spreadsheets as well. So the payments of $100 from Grandma. If you want, you can go ahead and format the currency to be dollars. It's nice to do that. Okay. I like payments at time 1, time 2, time 3, etc. to all be 100. Now I could just type $100 and copy and paste that. But again, I'm trying to tie it to what's in cell B2 to make updates. If I type equals B2 here, that will work in cell B6. But the copying and pasting will get messed up for the other cells. Watch it here. The copying and pasting will get messed up because there's nothing in cell B3, so you see nothing in cell B7. And there's the word payments in cell B4, so you see the word payments in cell B8. I don't want that. So what should I do instead? I need to use Excel or Google Sheets way of creating what are called absolute cell references or fixed cell references, you use dollar signs to do it. But the dollar signs don't represent money. A dollar sign in front of a B here will fix the column. A dollar sign in front of the 2 will fix the row. And actually, if I'm only copying and pasting downward, the column would automatically be fixed. So I really only need the second dollar sign. But if you kind of want to just play it safe, you can include both. There's some circumstances where you might want to just include one for sure. But here it doesn't hurt to include both. And now when I copy and paste that down, it does not get updated. It stays equals B2 the entire time. And that's why you see a bunch of hundreds now. That's an absolute cell reference. Use dollar signs for absolute cell references. Don't use dollar signs if you want the formula to get updated. And the dollars there don't mean money. PVs, present values. Okay. What did I do by hand? I kept dividing by higher and higher powers of 1.02. Do the same thing here, except use the cell references, A2, and maybe these, the times. But be careful, you want A2 to be a fixed cell reference because you always want to use the 0.02. By the way, if you didn't notice there, I didn't type B6, I just clicked on cell B6 like this. That's nice. Divide by, I better play it safe with extra parentheses here. 1 plus the interest rate R is in cell A2, but I want that to stay always A2 as I copy and paste downward. So use dollar signs. To the T power. I'm trying to play it safe with parentheses just in case. So this is going to be the 100 divided by 1.02. That was about $98.04. Ready? There it is. It's actually showing me already what the other ones are, and I could do an autofill, but let's do it by clicking and dragging the lower right corner. The next one was 100 divided by 1.02 squared. That was $96.12. That's what I wrote down. There it is. 96.12. The next one's $94.23. There it is. And then I can keep going. Fun, fun, fun. If you go far enough, hundreds or thousands of rows down, then it's really fun because you're going really fast or whatever. You got to say, wee, when you do that kind of thing. Notice these amounts keep getting smaller. These present values keeps getting smaller because I keep dividing by bigger powers of 1.02. $100 payments that are further in the future have smaller present values because they have more time to grow if you invested them. What's the total PV of all the payments? Just add them up. Equals SUM will add things up. You can type the cell references in a certain way. You can also just highlight them like this. C6 colon C25 could have been typed instead. Grandma's paying you nominal dollars, $100 every year for 20 years, $2,000 total. But the present value is smaller because it could be invested. And yeah, now it's set up that I could make changes. I could change the interest rate. What if it was an 8% interest rate? Would the present value go up or down? Got a guess for up. Got a guess for down. Should we vote? How many say up? Will the present, I increase the interest rate. Will the present value go up? How many say yes? Will it go down? How many say yes? Okay. Yep, it does go down because I keep dividing by bigger powers of 1.08, which means dividing by bigger numbers. Yeah, goes down. Get real extreme, like a 50% interest rate, it goes way down. What about future values? By hand, I multiplied by 1.02 to positive powers. What positive powers? I wanted to find the future value of time 3 at the end, the last payment, time of the last payment. Pretend you want to find the future value at the time of the last payment for grandma's payments, meaning at time 20. Careful here. I'm after the future value at time 20. This particular payment in row 6 is at time 1. How many years does it have to grow? 20 minus t. It's 19 years in this case. 20 minus A6. And notice I'm using dollars for the A2 because I want that to stay fixed. You might wonder, couldn't I just refer to the payment in cell B2 all the time instead of doing a B6 or B7 or B8? Yeah, the answer is yes, you could in this context with a level payment. But if we wanted to change the amount of the payment, it would be good to use what's in B6 as you see here. And yeah, 20 minus A6 is 20 minus 1 is 19. Mm-hmm.
I just realized what it detect glitch out of it at t=20 because that would be the 0th power.
Let's see what happens. I forgot a times in here. I think that's the problem. There we go. Okay. Let's see what happens. It's matching. Yeah, it's 100 times 1.08 to the 0 power, 100 times 1. If it's got more time to grow, the future value is higher. What's the total future value? Actually, I don't have to retype equals SUM. Turns out I actually can just copy and paste what's in cell C2 over to cell D2. In C2, we were adding up the numbers in column C. If I copy and paste that formula over here, it'll add up the numbers in column D. More than $2,000. Make sense? Also notice I could also do this. I could take the total present value times 1.02 to the 20th power, and I would get the total future value. Ready? Watch it here. Yep. So we could do with spreadsheets. How about Mathematica? And how about by hand? Mathematica first. If we're going to do it with Mathematica, we need a summation button instead of an integral button. Here's the summation button. It's next to the integral. I've got 20 numbers that are being added. I could start K at 1 and go up to 20. What are those numbers? For present values, they are 100 divided by 1.02 to different powers. First power, then second power, then third power, kth power in general. This is going to be the present value. This should be the 1600 something. Yep, 1635.14. 1635.14. There we go. We got a match. And for the future values, do 100 times 1.02 to the K, or 20 minus K. Although if we did a K power, we'd get the same answer because it's still K is still ranging from 1 to 20. No, it actually doesn't get the same answer. I'd have to let K go from 0 to 19 to get the same answer. It's simpler to think of it this way. 24, 29, 74. Is that a match? 24, 29, 74. There we go. So Mathematica is quicker, but the spreadsheet does give you more information. It tells you all the present and future values of all the payments, which if you're interested, you could then see. How about by hand? By hand, we need the formula for a finite geometric series. And series in this context is synonymous with the word sum. In this context, those two words, series and sum, are synonyms. Of course, in other contexts, they may not be synonyms. Geometric series are sums of a special form. In our textbook, they're written as this form. Some number A plus another number obtained from A by multiplying by a certain number. That other number we multiply by is called X in our textbook. Other books call it R. Plus another term obtained by multiplying by the same number X to get AX squared, or AR squared if you're using the letter R. Plus AX cubed, etc. If it's a finite geometric series, this will stop sometime. And if I'm saying there are finite geometric series, that must mean there are infinite geometric series? Yes. We'll talk about those starting Wednesday. What's the last term? It turns out there are different conventions you can use. Our book uses the convention that it wants n terms in the sum. Since the first term has a, which is the same as a times x to the 0 power, the nth term will be a times x to the n minus first power. So a is the first term or leading term. X is called the common ratio. The word ratio means fraction. So why is X a fraction? Well, it's because if I take any one of these terms except the first one and divide by the preceding term, like AX cubed divided by AX squared, the A's cancel and X squareds cancel, leaving you with an X. That's the ratio that's always common. Every time you take a term except the first one and divide by the previous one, you get X. And n is really the number of terms. What are we after? We're after what's called a closed formula for this. What a closed formula is it's a formula that does not involve plus dot, dot, dots. Or if I decided to write this in summation notation, it does not involve a summation sign. If I did write it in the in summation notation, the two most common ways to write it are like this. K goes from 1 to n of a times x to the k minus 1. That's one way to write it. It's not a unique way to write it. In fact, there's infinitely many ways to write it. But the other most common way to write it would be to start at k at 0 and go up to n minus 1 of a times x to the k. Those two summations, even though they look different, really mean the same thing. Question?
Will the process of finding this be similar to back substitution for discrete?
Fact substitution, is that what you call it? Back substitution. Not sure because I haven't taught discrete. So maybe. It is going to be pattern recognition and doing some arithmetic, some algebra. And these are, have you talked about generating functions in discrete?
I took it last fall, but I
Okay, that
don't
sound
think
familiar?
so.
Okay. If you know about generating functions, these are similar, but if you don't worry about it. I'm going to give this a name, a shorthand name. I'm going to call it S sub n, S for sum, subscript of n for the fact that there's n terms. To find a closed formula for this, without dot dots, without dot dot dots, and without a summation sign, use a little trick. And the trick is to multiply both sides of this by x. On the left, it gives me x times Sn. On the right, it gives me ax, a times x, plus ax times x, which is ax squared. I just multiply every term by x, ax cubed, ax to the fourth, etc. The second to last term would be ax to the n minus 1, obtained by multiplying ax to the n minus 2 by x. And then the very last term is going to be ax to the n. And because of the patterns here, you can quickly see that these terms in the first summation match these terms in the second one. And therefore, if you subtracted one equation from the other, you get a bunch of cancellation. Let's subtract the bottom one from the top one. Sn minus x times Sn. A bunch of stuff cancels. The only things that don't cancel are the a and minus ax to the n. My goal is to solve for Sn. Over there, I can factor out an Sn like this. And then I can divide both sides by 1 minus x. There's the answer. More typically, you factor an a out of the top and write it like this. There's your closed formula for this finite geometric series. Of course, we don't want to divide by 0 here, so this is assuming x is not equal to 1. Because otherwise you'd be dividing by 0. But wait a minute, couldn't we figure out the sum when x is 1? And the answer is you can. It's simpler. What is the answer, David? Yeah, if x is 1, then you're adding n a's. It's the same as a times n. If x equals 1, Sn is a, etc. And I'm assuming there's n of those terms. So that's the same as n times a. So it's simpler when x is 1. More interesting when x is not 1. And more useful, you could say. So what I'm trying to say here ultimately is we can do these problems using this formula instead. Still going to need your calculator, but if you don't have access to a spreadsheet or Mathematica, it's the quickest thing to do. So let's try the first example here to start with. And this is actually the previous class's page. I labeled A to be the first term. You might want to write that down. Okay, let's redo it here. There's your A. What's R? That's the hardest part. Or excuse me, what's X? Common ratio. Go ahead. It is 1.02 to the negative 1 power, or if you prefer 1 divided by 1.02, the reciprocal of 1.02. And n is the number of terms, that's 3. So the formula is going to give S3, which is the present value. A is really, yeah, well, I'll write it as a fraction. 100 divided by 1.02. X again is 1.02 to the negative 1 power. That's going to get raised to the third power. Divided by 1 minus x is 1 divided by 1 minus 1.02 to the negative 1 power. It is very easy to make a mistake with this. So be really careful. To maximize your partial credit, I would write down your intermediate answers. For example, 1 minus 1.02 to the negative 1 power is 0.019678. This is a 98.039216, and then 1 minus 1.02 to the negative 1 power cubed is the same as to the negative 3 power. Point 0.057677. Say. There we have it, 288.39, same answer. For the future value one, well, here's another thing about these geometric series. You can think of it, this is A or this is A. You can go left to right or right to left. It doesn't matter. Of course, it's more typical to think left to right. I could take this to be my A and X to be the same thing, 1.02 to the negative 1 power, and N is 3 still. So if I did that, actually the only thing that would change here would be the number in front. The 98 would become 104.04, I think. $104.04 is what I got there. So in this case, S3, yeah, it's going to be the same thing except for the number that's in the very front. There we have it, $306.04. That's the same thing we got before as well. Yeah, I could have done it right to left as well. I could have taken A to be 100. But then X would have been 1.02 to the positive 1 power, which is 1.02. N would still be 3. The details would be different, but the final answer would be the same. You should take the time after class to check that. And all this works when N is 20 as well. In fact, the numbers are the same except the N when N is 20. So coming back up here, if I keep everything but the 3 the same, just change the 3 to 20, what do I get? The bottom of this fraction still stays the same. What's 1 minus 1.02 to the negative 20 power? Oops. So this is the only thing that's changing up here. I get a 0.32702866669 instead of that thing. Still multiply by 98.039216, still divide by 0.0196078. This is the number that's a little less than 2,000. It's 1,600 something. Yep, 1635.14 or 15. We got with the spreadsheet, it should be 1635. Well, okay, it rounded to 14 there and 15 here. Probably because we didn't have enough decimal places in some spot. But it's within a cent. And I could do something similar here. Just change n to 20. Okay. What about going back to chapter 8, income streams? Money flowing into your bank account every single day, every hour of every day, every minute of every day, every second of every day, every millisecond of every day. Doesn't happen with any individual people except maybe, you know, Elon Musk or Bill Gates or whomever, some billionaire. It happens with big corporations like Amazon, Walmart, Apple. You know, they're getting probably thousands of dollars every second of every day. Seriously, going into their bank, wherever they keep their money. I don't even want to call it a bank necessarily. It's probably a bunch of banks. They're also paying money every second of every day too, right? They've got expenses. They're worldwide companies. So income streams and modeling income streams actually becomes a more realistic way of keeping track of their money. And they do need to think about present values and future values. But for the context of keeping things simple for you guys, let's imagine grandma again. Instead of giving you 3 $100 payments at these discrete times, 1, 2, and 3, she gives you money continuously every second of every day, so that the total amount still adds up to $300 over 3 years, meaning $100 per year. $100 per year. We want to get technical about it with leap year. Averages to that many dollars per day. Yeah, a little bit more than 1 cent per hour. $0.0114 per hour. That much per hour, meaning fractions of a cent per minute. Smaller fractions per second. Smaller fractions per millisecond. That's how many dollars per millisecond you're getting. 3.1688 times 10 to the negative 9 dollars per millisecond. Of course, she's not literally making those kinds of payments, but you could pretend. And in fact, it's probably simpler to pretend it's continuous if it were somehow literally every second, or even every hour, a little more than 1 cent an hour. It's probably simpler to model it as happening every second, every millisecond, every microsecond, whatever, every picosecond, nanosecond. I forget all the words. Is there a smallest unit of time? Planck constant, Planck unit of time, like something like 10 to the negative 30 something seconds. Yeah, yeah. Which does bring up philosophical questions. Is time continuous or is it discrete at heart? Well, it's certainly better to model it as continuous. Whether it really is continuous or not is another question. It's simpler to model as continuous. So in this case, P of T represents your income stream. It's a rate of payment. It's really a derivative of something. In, say, dollars per year. And in general, it might not be a constant rate. It could be a variable rate. It could be a function whose graph is not a horizontal line. But for grandma, it's going to be simplest to assume it's a horizontal line, $100 per year. And you could graph it. P of T in dollars per year. It's a horizontal line from time 0 to time 3. And again, what this, you got to make sure you interpret this correctly. This is just representing the fact that she's giving you effectively about what it turned out to be 1 cent per hour, approximately. Fraction of a cent per minute and a smaller fraction per second. So that the total amount paid to you nominally over 3 years is 100 times 3 is $300. But the $300 is not the present value, it's not the future value, it's just the nominal dollar amount in name only. It's not keeping track of the reality of the time value of money. We want the present value of this. How do we find that? I'll just put equals question mark to begin with. As always, get your knife out. Chop, 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 chop. What do we chop? The time interval into tiny little pieces. Say that this left endpoint is time t, and say the length of time is delta t. This is a rate of payment, dollars per year. It's constant, but even if it were not constant, even if it were a curve that was not a horizontal line, it still would be continuous, and you still could approximate the amount of money that she pays you during the small time interval by multiplying. P of T dollars per year times delta T years. This is a dollar sign here. Funny look, badly made dollar sign. Dollars per year times years. The years cancel. This is in dollars. That's a small amount of money that she pays you during a small amount of time. Small amount of money. Nominal. Small nominal, not taking time value money into account, amount of time, or excuse me, amount of money. What's the small present value of that small amount of money? Maybe call it delta PV. I have to discount this back to time 0. Multiply by 1 plus r to the negative t power. It's going to be handy for us to think of this as 1 over 1 plus r to the positive t power. It'll be handy for the purposes of integration. So this is the small present value. So the total present value of the entire income stream would be the sum of the small present values, sum of things that look like this. And as always, now we let delta t go to 0. And the total present value becomes an integral. By definition, integral of P of T times 1 over 1 plus r to the t dt. Interval of integration is 0 to 3. And in this problem with grandma paying you money, this is 100. And 1 plus r is 1.02. But to do the integral, well, we can do one of two things. We could either try to relate this to e, or we could use this derivative fact that you may or may not remember. The derivative with respect to t of, say, a to the t, where a is a constant, is natural log of a times a to the t. I think that did show up on Calc 1 gateways. The corresponding integral fact, integral of a to the t, is a 1 over natural log of a times a to the t plus c. That does not show up on the Calc 2 gateway. Anyway, this can be used here with a equal to 1 divided by 1.02. That was about 0.98. P of t is 100. So we get 100 divided by natural log. A is 1 divided by 1.02 times a to the t. A again is 1 divided by 1.02 to the t. That's going from 0 to 3. By properties of logarithms, natural log of 1 over 1.02 is the same as negative natural log of 1.02, and I can bring the negative sign out in front. And this is the same as 1.02 to the negative 3 minus 1.02 to the negative 0 power. That's a 1. Even though you got a negative sign in front, the final answer is positive because this part here is negative. And you know, it should be a little less than 300 in the end, right? Just like before. I know the negative signs can't have to cancel, but yeah, a little less than 300. 291.26. How about the future value at time 3? Instead of discounting back to time 0, we have to promote to time 3. We have to invest the money, so to speak. Instead of multiplying by 1 plus r to the negative t, we'll multiply by 1 plus r to a positive power. Careful what the positive power is, though. It's not t. It's 3 minus t. So we'll get a very analogous integral here. 0 to 3, p of t, except it's 1 plus r instead of 1 divided by 1 plus r. Not to the t power, but to the 3 minus t power. It doesn't make a difference here when you got a constant income stream, rate of payment. But it would make a difference if it was not constant, to make sure you have a 3 minus t there. Once again, this is still 100. This is still 1.02. Careful here. You're going to get 100 over natural log of 1.02. And the negative sign there is going to lead to a negative sign out in front. But the final answer still will be positive. Interesting, the factors in front are the same. But this time you got 1.02 to the 0 power minus 1.02 to the 3rd power. This should be in the end something a little bit bigger than 300. That's a 1. Yep, about 309. That's if R is given as an effective annual interest rate. But these are not actually the formulas that you'll find in the book. The formulas in the book involve the number E. They still involve an R, but in the context when the formulas involve E, let me show you them here. Here they are. The R in this case means something a little different. Instead of an effective annual interest rate, the R in these formulas represents something called a continuous annual interest rate, not effective. What's the difference? The effective annual interest rate is effectively the actual interest you get, what you really get. The continuous annual interest rate is an equivalent interest rate that still gives you the same final amount in the end. It's just a different way of modeling it. You're imagining compound interest where the compounding is happening every second of every day, every millisecond of every day. The values of R are related, but they're not exactly the same. They're close together, but they're not exactly the same. To convert from one to the other, like if our effective interest rate is 2%, 2% effective interest rate, to convert to a continuous interest rate, where R here is the continuous interest rate, I'm assuming in both cases these are annual. I want to solve for R in the equation e to the R equals is 1.02. Now what that means is R is natural log of 1.02. Which is a little less than 0.02. 0.0198. What this is telling you is a 1.98% continuous interest rate. If money was being compounded every millisecond of every day, is equivalent to a 2% effective interest rate. Your money, in the simplest situation of just depositing the money in an account and letting it sit for a year, if that's your continuous interest rate, your money actually grows by 2%, not 1.98%. So you do have to look in the book when you got your homework problems. Is the interest rate you're giving me an effective annual rate? They may not put the word effective in there, right? They might just say it's the annual rate. Or is it saying it's a continuous rate? If it's a continuous rate, just use these formulas straight away as they are, with R being the continuous interest rate. If it's an effective annual interest rate, you can do one of two things. You can either do what we did in these problems with these integrals, or you can convert your effective interest rate into a continuous interest rate and then use the other formulas in the book involving E. How's it come up in homework? Let's just take a glance at a few homework problems. I don't know for sure which ones I'm going to assign yet. For example, number 6 that says a 2% interest rate per year compounded continuously. That's a signal to use R equals 0.02 and the formulas involving E. In fact, most of these are saying compounded continuously. Do any of them not? I mean, the first couple did not. Compounded annually. Looks like 21 is saying assuming an annual interest rate 2%. They don't put the word continuous in there. So I think that's assuming it's effective. Here they don't put the word continuous in there either. So I think that's probably assuming it's effective. I mean, yeah. If they don't put the word continuous in there, should you assume it's effective? I think so. Maybe I should check a few of these answers that are odd in the back of the book just to make sure. But I think if they don't put the word continuous in there, then assume it's effective. I'll do it in fairly short order here this afternoon and get back to you with a message. Okay. All right. Have a good day.